Hello and welcome to our astronomy course. Today we will be Kevin and lecture number 2 from the period. Okay, and the topic of today's lecture very simple and maybe ordinary for many of you, the sun. But believe me, it's very interesting. The sun is the source of light and warmth in our solar system. So it is a natural object of human curiosity. It is also the one star that is most clearly visible from our planet. The interaction of light and matter, which you studied earlier, can reveal the secrets of the sun and introduce you to the star. In this lecture, you will discover how the analysis of the solar spectrum can paint a detailed picture of the sun's atmosphere, and how basic physics has solved the mystery of the sun's form. Here you will answer 4 essential questions. What do you see when you look at the sun? How does the sun make its energy? What are the dark sunspots? And why does the sun go through a cycle of activity? At once, know a lot more about the sun if it were farther away. The sun is so close to Earth's astronomers and can see remark that solar astronomers would swirling currents of gas and arch bridges of magnetic force. The details seem overwhelming, but the sun is just an average star, and in a sense, it is a simple object. It is made up almost entirely of the gases hydrogen and helium, confined by its own gravity in a sphere of 109 times Earth's diameter. The gases of the sun's surface are hot and radiate the light and heat that make life possible on the Earth. That solar atmosphere is where you can begin your exploration. The sun's atmosphere is made up of 3 layers. The visible surface is the photosphere, and above fly the chromosphere and corona. When you look at the sun, you see a hot, glowing surface with a temperature of about 55800 Kelvin. At that temperature, every square millimeter of the sun's surface must be radiate more energy than a 60-watt light bulb. With all that energy radiated into the space, the sun's surface would cool rapidly if energy did not flow up from the interior to keep the surface hot. So, simple logic tells you that energy in the form of heat is flowing outward from the sun's interior. Okay? Not until the 1930s did astronomers understand that the sun makes its energy by nuclear reactions at the center. These nuclear reactions are discussed in detail later in this lecture. For now, you can consider the sun's atmosphere in its wisdom, average state. Later, you can add the details of its continuous activity as heat flows outward from its interior and it churns like a pot of boiling The visible surface of the sun looks like a smooth layer of gas marked only by a few dark sunspots that come and go over a few weeks. Also, the photosphere seems to be a distinct surface. It is not solid. In fact, the sun is gaseous from its outer atmosphere right down to its center. The photosphere is the thin layer of gas from which the Earth receives most of the sun's light. It is less than 500 kilometers deep and has an average temperature of about 5,800 centigrade. If the sun magically shrunk of the size of a bowling ball, the photosphere would be no thicker than a layer of tissue paper wrapped around the ball. The photosphere is the layer in the sun's atmosphere that is dense enough to emit plenty of light, but not so dense that the light can't escape. Below the photosphere, the gas is denser and hotter and therefore radiates plenty of light. But that light cannot escape from the sun because of the outer layers of gas. Are you agree with me? Okay, nice. So, you cannot detect light from these deeper layers. Above the photosphere, the gas is less dense and is unable to radiate much light. Also, the photosphere appears to be substantial. It is really a very low density gas. Even in its deepest and densest layers, the photosphere is 3,400 times less dense than the air you breathe. Yeah. To find gases as dense as the air at Earth's atmosphere, you would have to descend about 70,000 kilometers below the photosphere, about 10% of the way to the sun's center. With fantastically efficient insulation, you could fly a spaceship right through the photosphere. The spectrum of the sun is an absorption spectrum, and that can tell you a great deal about the photosphere. You know from Kirchhoff's third law that an absorption spectrum is produced when a sort of continuous spectrum is viewed through a gas. In the case of a photosphere, the deeper layers are dense enough to produce a continuous spectrum, but atoms in the photosphere absorb photons of specific wavelength, producing absorption lines of hydrogen, helium, and other elements. In this slide, absorption lines you can see is exactly vertical black line. Right? Okay. In good photographs, the photosphere has a mottled appearance because it is made up of dark edge regions called granules. The overall pattern is called granulation. Let's see in this figure, please. Each granule is about the size of Texas and lasts for only 10 to 20 minutes before fading away. Faded granules are continuously replaced by new granules. Spectra of these granules show that the centers are a few hundred degrees hotter than the edges, and Doppler sheets reveal that the centers are rising and that edges are sinking at speed of about 0.4 kilometers per second. From this evidence, astronomers recognize granulation as the surface effect on convection just below the photosphere. Convection occurs when hot fluid rises and cool fluid sinks, and when the example of convection, current of hot gases rises above a candle flame. You can watch convection in a liquid by adding a bit of cool non-dairy creamer to an unstirred cup of hot coffee. The cool creamer sinks, boils, expands, rises, cools, contracts, sinks again, and so on, creating small regions on the surface of the coffee that mark the tops of convection currents. Viewed from above, these regions look much like solar ground. In the sun, rising currents of hot gas hit small regions of the photosphere, which, being slightly hotter, emit more black body radiation and look brighter. The cool sinking gas of the edges emits less light and thus look darker, as you can see in this slide. The presence of granulation is clear evidence that energy is flowing upward through the photosphere. Spectroscopic studies of the solar surface have revealed another less obvious kind of granulation. Supergranules are regions a little over twice Earth's diameter that include about 300 granules each. These supergranules are regions of very slowly rising currents that last a day or two. They appear to be produced by larger currents of rising gas deeper under the photosphere. This visible image of the sun at the left part of the slide shows a few sunspots and is cut away to show the location of energy generation at the sun's center. The Earth's moon system is shown for scale. In Greek mythology, the sun was carried across the sky in a golden chariot pulled by powerful horses and guided by the sun god Helios. When Phaeton, the son of Helios, drove the chariot one day, he lost control of the horses, and Earth was nearly set ablaze before Zeus smote Phaeton from the sky. Even in classical times, people understood that life on Earth depends critically on the sun. Above the photosphere lies the chromosphere. Solar astronomers define the lower edge of the chromosphere as lying just above the visible surface of the sun, with its upper regions blending gradually with the corona. You can think of the chromosphere as an irregular layer with a depth of average less than Earth's diameter. See this slide. Because the chromosphere is roughly thousands times fainter than the photosphere, you can see it with your unaided eyes only during a total solar eclipse, when the moon covers the brilliant photosphere. Then the chromosphere sphere flashes into view as a thin line of pink just above the photosphere. The word chromosphere comes from the Greek word chroma, meaning color. The pink color is produced by the combined light of three bright emission lines: the red, blue, and violet Balmer lines of hydrogen. Astronomers know a great deal about the chromosphere from its spectrum. The chromosphere produces an emission spectrum, and Kirchhoff's second law tells you it must be an exciting, large density gas. The chromosphere is about 110 times less dense than the air you breathe. Spectra reveal that atoms in the lower chromosphere are ionized, and atoms in the higher layers of the chromosphere are even more highly ionized. That is, they have lost more electrons. from the ionization state of the gas, astronomers can find the temperature in different parts of the chromosphere. Just above the photosphere, the temperature falls to a minimum of about 4,500 Kelvin and then rises rapidly, as you can see in this slide, to the extremely high temperatures of the corona. Solar astronomers can take advantage of some elegant physics to study the chromosphere. The gases of the chromosphere are transparent to nearly all visible light, but atoms in the gas are very good at absorbing photons of specific wavelength. This produces certain dark absorption lines in the spectrum of the photosphere. A photon at one of those wavelengths is very unlikely to escape from deeper layers. A filtergram is an image of the sun made using light in one of those dark absorption lines. Those photons can only have escaped from higher in the atmosphere. In this way, filtergrams reveal detail in the upper layers of the chromosphere. Another way to study these high layers of gas is to record solar images in the far ultraviolet or in the X-ray part of the spectrum. This figure shows a filtergram made at the wavelength of the H-alpha Balmer line, H-alpha or hydrogen alpha image, as you can see in this part of the slide. This image shows complex structure in the chromosphere. Cycles are flame-like jets of gas extending upward into the chromosphere and lasting 5 to 15 minutes. Seen at the limb of the sun's disk, these cycles blend together and look like flames covering a burning prairie, but they are not flames at all. Spectra show that specules are cooler gas from the lower chromosphere extending upward into the hotter region. Images at the center of the solar disk show that specules spring up around the edge of the supergranules, like weeds around flagstones, as you can see on this slide. Spectroscopic analysis of the chromosphere alert you that it is a low-density gas in constant motion, where the temperature increases rapidly with height. Just above the chromosphere lies even hotter gas. The outer part of the sun's atmosphere is called the corona, after the Greek word for crown. The corona is so dim that it is not visible in Earth's daytime sky because of the glare of scattered light from the sun's brilliant photosphere. During a total solar eclipse, however, when the moon covers the photosphere, you can see the innermost part of the corona, as shown in this figure. Observations made with specialized telescopes called coronagraphs can block the light of the photosphere and record the corona out beyond 20 solar radii, almost 10% of the way to Earth. Such images show screamers in the corona that follow magnetic lines of force in the sun's magnetic field. Let's look at this picture. The spectrum of the corona can tell you a great deal about the coronal gases and simultaneously illustrate how astronomers analyze a spectrum. Some of the light from the outer corona produces a spectrum with absorption lines that are the same as the photosphere spectrum. This light is just sunlight reflected from dust particles in the corona. In contrast, Some of the light from the corona produces a continuous spectrum that lacks absorption lines, and that happens when sunlight from the photosphere is scattered or free electrons in the ionized coronal gas. Because the coronal gas has a temperature over 1 million Kelvin, and the electrons travel very fast. The reflected photons suffer large random Doppler shifts that smear out absorption lines to produce a continuous spectrum. This continuous example of a continuous spectrum you may see in these exactly slides. Superimposed on the corona's continuous spectrum are emission lines of highly ionized gases. In the lower corona, the atoms are not as highly ionized as they are at higher altitude. And this tells you that the temperature of the corona rises with altitude. Just above the chromosphere, the temperature is about 500,000 Kelvin. In the outer corona, the temperature can be 2 million Kelvin or even more. The corona is exceedingly hot gas, but it is not very bright. Its density is very low, only 106 atoms per cubic centimeter in its lower region. That is about 1 trillion times less than air you breathe. In its outer layers, the corona contains only 1 to 10 atoms per cubic centimeter, fewer than in the best vacuum on Earth. Because of this low density, the hot gas does not emit much radiation. Astronomers have wondered for years how the corona and chromosphere can be so hot. Heat flows from the hot regions to cool regions, never from cool to hot. Okay? So, how can the heat from the photosphere with a temperature of only 5,800 Kelvin flow out into the much hotter atmosphere and corona? Observations made by the SOHO satellite have mapped a magnetic carpet of looped magnetic fields extending up through the photosphere. Remember that the gas of the chromosphere and corona has a very low density, so it can't resist movement of the magnetic field. Turbulence below the photosphere seems to flick the magnetic loops back and forth and whip the gas above the heating gas. Furthermore, observations with the Hinoid spacecraft have revealed magnetic waves generated by turbulence below the photosphere traveling up into the chromosphere and corona and heating the gas. In both cases, energy appears to flow outward as the agitation of the magnetic field. Not all of the sun's magnetic field loops back. Some of the fields lead outward into the space. Gas from the solar atmosphere follows along the magnetic field that point outward and flows away from the sun in a breeze called the solar wind. Like an expansion of the corona, the low-density gases of the solar wind blow past Earth at 300 to 800 kilometers per second, with gusts as high as thousands kilometers per second. Earth is bathed in the corona's hot breeze. Because of the solar wind, the sun is slowly losing mass. But this is only a minor loss for an object as massive as the sun. The sun loses about 10 in power 7 tons per second. But that is only 10 in power minus 14 over solar masses per year. Later in life, the Sun, like many other stars, will lose mass rapidly in a more powerful beam. You will see in future chapters of our lecture how this effect starts. Do other stars have chromosphere, corona, and stellar wings like the Sun? Stars are so far away, and they never look like more than point of light. But ultraviolet and X-ray observations suggest that the answer is yes. The spectra of many stars contain emission lines in the far ultraviolet that could have formed only in the low density, high temperature gases of a chromosphere and corona. Also, many stars are sources of X-ray, which appear to have been produced by the high temperature gas in corona. This observational evidence gives astronomers good reason to believe that the Sun, for all its complexity, is a typical star. The layers of the solar atmosphere are all those astronomers can observe directly. But there are phenomena in those layers that reveal what it's like inside the Sun, your next destination. Almost no light emerges from the below the photosphere, so you can't see into the solar interior. However, solar astronomers can study naturally occurring vibrations in the Sun to explore its depths in a process called helioseismology. Random convective movements of gas in the Sun constantly produce vibrations, rumbles that would be much too low to hear with human ears, even if your ears could survive a visit to the Sun's atmosphere. Some of these vibrations resonate in the Sun like sound waves in organ pipes. A vibration with a period of 5 minutes is strongest, but the periods range from 3 to 20 minutes. These are very, very low pitched sounds. Astronomers can detect these vibrations by observing Doppler shifts in the solar surface. As a vibrational wave travels down into the Sun, the increasing density and temperature carve its path, and it returns to the surface, where it makes the photosphere cave up and down by small amounts, roughly plus or minus 15 kilometers. This covers the surface of the Sun with a pattern of rising and falling regions that can be mapped during the Doppler effect, like at this slide. By observing this motion, astronomers can determine which vibrations resonate and become stronger and which become weaker. Short wavelength waves penetrate less deeply and travel shorter distances than longer wavelength waves. So, the different wavelength vibrations explore different layers in the Sun. Just as geologists can study Earth's interior by analyzing vibrations from earthquakes, so solar astronomers can use helioseismology to explore the Sun's interior. You can better understand how helioseismology works if you think of a dark pond. If you stood at the shore of a dark pond and looked down at the water, you would see ripples arriving from all parts of the pond. Because every dot on the pond contributes to the ripples, and you could, in principle, study the ripples near the shore and draw a map showing the position and velocity of every dot on the pond. Of course, it would be difficult to untangle the different ripples. So you would need lots of data and a big computer. Nevertheless, all of the information would be there lapping at the shore. Paleoseismology demands huge amounts of data, so astronomers have used a network of telescopes around the world operated by the Global Oscillation Network Group, GONG, Global Oscillation Network Group. The network can observe the sun continuously for weeks at a time as Earth rotates. The sun never sets on the GONG. The SOHO satellite in space can observe solar oscillations continuously and can detect motions as slow as 1 millimeter per second. Solar astronomers can then use high-speed computers to separate the different patterns on the solar surface and measure the strength of the waves at many different wavelengths. Paleoseismology has allowed astronomers to map the temperature, density, and rate of rotation inside the sun. They have been enabled to detect great currents of gas flowing below the photosphere and the emergence of sunspots before they appear in the photosphere. Paleoseismology can even locate sunspots on the backside of the sun, sunspots that are not yet visible from Earth. What evidence leads astronomers to conclude that temperature increases with high in the chromosphere and corona? Scientific arguments usually involve evidence, and in astronomy, that means observation. Solar astronomers can observe the spectrum of the chromosphere, and they find that atoms that are more highly ionized or have lost more electrons. I agree with you. Okay. Then atoms in photosphere. Atoms in the corona are even more highly ionized. That must mean the chromosphere and corona are hotter than the photosphere. Evidence is the key to understanding how science works. Now, it is time to build a new argument. What evidence leads astronomers to conclude that other stars have chromosphere and corona, like those of the sun? Do you have any questions or propositions? I hope you enjoyed this lecture, and I am looking forward to seeing you next time. Bye.